What is up, everybody? Welcome back to another weekly live stream on a Wednesday. And I am coming to you live from my new spot. So we're going to be continuing these weekly live streams, and we're still focusing on SAT problems from Khan Academy. And as I mentioned last week, we've gone through all of the practice tests already on Khan Academy. So now what's happening is I went through every single math section in the practice section for Khan Academy as far as the practice problems. But people have asked me to please go back and do the higher level problems, because what happens is after you do 5 problems, then it jumps to another 5 and the level moves up. So that's what I'm doing. I'm sort of going back through all the problems in this practice section that you can see up here, and doing them again for the second set. I'm calling these level 2. I'm going to do it again through level 3 and then level 4. And there's about 4 levels of problems for each one of these little mini sections. So last week we did interpreting linear functions. This week we're going to do linear equation word problems. So let's jump right in here. These are not timed, and so it's not going to be as fun as when we do the practice test. But the upside is it'll give me longer time to give good, solid explanations. So let's start with this one. It says a meteorologist estimates that on a sunny day, the air temperature decreases by about 4 degrees for every 1,000 feet. So every 1,000 feet, we're going down. The air temperature drops by 4. Every 1,000 feet we go up. Every elevation gain, we're going down by 4,000. On a certain day, the air temperature outside an airplane flying above Seattle is negative 58. And on the ground level, okay, all the way down here, it's 70. If X is the height above Seattle, so here's ground level. X is the height above Seattle. In feet, which the plane is flying, which of the following best models the situation? So before we even look at these problems, let's think about it a little bit. So basically what's happening is every 1,000 feet we're dropping by 4. So you can think about it as like the slope is essentially, if we look at these as y-axis or something, it's like if we consider, let's say, the temperature. I'm just going to kind of make this up here. Let's consider you could do it either way, but I'm going to say based on this, it looks like they do they're using, in some of these examples, they're using the temperature as the y value. So let's say temperature, and let's say elevation. So this is just one example. We'll say the slope is every time we go down 4, the elevation is going up by 1,000. So that means the slope is negative 4 over 1,000. Okay? And in this case, again, it is times our x. So our slope is this, negative 4 over 1,000. And remember, when x is 0, and we're talking about being the height going up to where this plane is. When elevation is 0, this is going to be 70. So let's think about it like this. We've got, let's see, so you got negative 4 over 1,000 times x plus 70 equals, and then what are we talking about? That would equal basically our negative 58. And then this is basically our target temperature, but we're having negative 58 here. Let's not even put 58 in yet. First, let's put in just our y. Okay, where y is the elevation, and that's what we're trying to find. This is essentially what models our situation, and then we want to know at what is the height for this guy when it hits negative 58. Now, if you're not sure, now that I set this up, this looks a little crazy, and I even want to know, did I actually do this right? Because we can get a rough idea. I erased too many things. Let me keep that up here. So let's see if we get a rough idea. Now look, we can also sort of not even do this necessarily algebraically, but we can count this out and sort of figure it out. Think about how many times we are going up by 4 to get to 58. All we got to do is take that difference, which is 70 plus 58. It's a difference of 128. So that's how many degrees we're going up, or going down by, Divide that by 4, and we should get 32. So that means that the answer to this, if we set this up correctly, I can already tell you the answer to this should be about 32,000 feet. That's how far. That's how high up. That actually kind of makes sense. The good thing about the SAT, they usually use values that are relatively realistic. 32,000 is about 6 miles up in the air. Wait, does that sound right? Does that sound crazy? So, anyways, 32,000 is the value that we would get. Let me just make sure that's right. 1,000, right? I think that's about right. Now, let's look at this value and see what would happen. This is no calculator, by the way, so you can't necessarily do it wouldn't be super easy to do this verification, but we could try it. So if we plugged in 32,000, would this work? Right? Divided by 1,000, that goes away, times -4, that would give us -128 plus 70. And indeed, it would give us -58 on the right side. So that I'm feeling pretty confident that this is our equation. But when I looked over before, I didn't actually see this equation. I saw something close to it. I saw these guys. So the question is, how do we get from this equation to one of these guys? Well, all they did was they moved the location of the 70, or in this case, they left the 70 right here. They got a positive 70 in both of these, and they moved this guy over. So how do we move that guy? We add 4 over 1,000x to both sides. Let me make some room here. We don't need this guy anymore. So what do we get now? We get 4 over 1,000x minus 58 equals 70. And I believe that is B. All right, it's just a flip-flop the sides. Well, let's see if that is indeed correct. And that is correct. Right? And look, this choice is almost good, but they got the wrong. The slope is negative if it's in the original setup, but once you move things around, it changes. So that was a pretty complex one. You can see how the level, if you remember the first time I went through this topic, you can see how these are getting more difficult. All right, let's try this one. A taut string. Taut is a tightly kind of held up string that's high tension. A taut string of length 10 inches is plucked at the center. The vibration travels along the string at a constant rate, c inches per milliseconds in both directions. I'm just going to say c per millisecond. C inches per millisecond. Just making my little notes. If x represents the position on the string from the leftmost end, x represents the position on the string from the leftmost end. Oh, and I see. And then this is, so here would be 0, here would be 10, right? And that's x. Which of the following equations can be used to find the location of x, the location x of the vibration after 0.3 milliseconds? So essentially, we don't know what c is, but we can. I can tell you that. Look, if we want to get the distance, all right, we can kind of look and see like, well, how do we get the distance? Distance equals rate times time. So our rate is c. Our time is, what is it? 0.3. Let's do it like this. So c times 0.3 is going to equal our distance. Okay. But they've obviously got some absolute value things going on in here, because we're going to have two locations. We're going to have a distance. Oops. We're going to have a location here, and we're going to have a location here. And so what we can kind of think about is, how is this going to be? It's going to be like a positive 0.3. I'm sorry. It's going to be like a positive c and a negative c. So we can also say negative c times 0.3 equals d. But we have to be a little bit more careful in exactly how we're doing this. So what exactly is happening? Actually, let me scroll down and look at some of these answers. So what they're doing here is they're taking the absolute value of 10. I don't know if I like this guy. All right, so I'm going to think this through a little bit further. This is actually pretty tough. So let's see. If we basically say, so we've got our distance right here, c times 0.3, and we want to get the distance going in both of these directions. And what we should be ending up with is, and so x is going to be from 0 to 10. So at like point, I'm gonna try and think about this for a second, because at 0.3 seconds, let's say, if c were 1, we should actually be 0.3 inches here. So we should be at the, and this would be the 5, this would be the 5 mark right here. We should be at 5.3 and like 4.7. Those would be the two answers. Let's see here, C.3C. So I think what we're looking at is, I'm kind of going by elimination to a certain degree. I see how we can kind of think about it. Okay. I'm feeling like it's gonna be A, but let's break this down a little bit farther. So I'm gonna explain why I think it's gonna be A. Having to use some reverse logic, because I'm not feeling totally confident about exactly how to set this up straight up. So I'm trying to use a different approach. So again, remember I said c times 0.3 is that distance, so it's like x minus 5, which is the position, right? This is our distance, equals 0.3 times c. If we distribute that c over here, we multiply both sides times c. So the reason why I'm feeling like this is right is because what's happening is they're saying that this is the distance from 5, right? So this would be the distance from 5. This would be the distance from 5. And or we're taking the total location. Let's say this would be like 5.3. This would be like 4.7. And then this would give you the same value in either case when we're subtracting from 5 from that center, which is basically the equivalent of our distance that is traveled, which is this guy, which is why I'm like an A. Now I don't think that's the greatest explanation as far as coming up from scratch, but let's go ahead and see if that was actually the correct answer. Okay, and it is. I'm going to just go through their explanation. So here's what they're saying. Yes. So again, it's the absolute value. This is the distance from the center, which is represented by this. And then this is the same thing that they say. This is the distance, which is 0.3c, which is distance equals rate times time. And then they just set the two equal to each other. And then it was just, for whatever reason, they divided by c, or multiplied by 1 over c. Okay. That was hard. Let's go to the next one. Question 3. In the year 2006, the average home price per square foot of a certain county was $98. This is in 2006. For each year before or after 2006, the average price per square foot increased year before or after. Oh, so it's always increasing by $350. And for each year before or after. Oh no, it's always increasing by 3.5. So when is it going to be 119? I mean, in what years could the average home price per square foot be 119? Oh yes, yeah. So it's going up in both directions. Well, I mean, a fast way we can do this is just basically take the difference and then divide it by 3.5. And this is a calculator section, so you could do that, but I'm guessing you can do this without a calculator. So this ends up becoming 21 over 3.5. 21 divided by 7 is 3. 21 divided by half of 7 should be 6. So that means it would be 6 years away from this up and down. So it should be 2012 and 2000. So that's what I'm feeling like is a pretty clear-cut answer. I didn't even need to necessarily set up an equation, but that seems to be right. Yeah. All right, we got it. Question number 4. Oliver mows lawns in his neighborhood. He charges $10 for each regular lawn he mows, and charges an extra 5 for each large yard he mows. So 15 times L, I guess. In 1 week, he mowed 6 more large yards than he did regular yards. So this is a system of equations, I guess. So in this week, the large ones equaled to 6 more than the regular ones. Let's make this R, not M. And he made 200. So this is our first equation. Then he made L times, 10 times R, that's how much he's making from the regular, plus 15 times L equaled 265. If R represents the number of regular yards that Oliver mowed, what equation best models the situation? And these are equations with just R. Now, look, we have a great equation here, but it's got an L in it. So what do we need to do? We need to do a little substitution and get rid of that L. So this ends up becoming 10R plus 15 times, replace L with R plus 6 equals 265. And let's say you don't even need to solve, which is nice. They just want you to get the equation. And it looks like C is our answer. Let me make sure. 15. Yeah. The difference between C and D is they got 5 here instead of 15, so this should be good. And we're good. All right, last one. Number 5. A popular candy is manufactured to weigh 0.16 ounces per piece. 0.16 ounces per piece. Actually, let me get the ounces per piece. The pieces are sold in packages of 36. I'll just say this is 36, using the good old bar model from Singapore math. If the allowable amount of variation in weight for one piece of candy is 0.03 ounces, that means each one can be as high as 0.19, as low as 0.13. That's all it means. Right, we're adding 0.03 to this and subtracting 0.03 from this. Which of the following equations can be used to determine the highest and lowest allowable weight, W, of a package of 36 pieces? Okay, so here's what this is all about. The weight, they're saying the weight minus 0.16, the difference between the weight and 0.16 has to be less than, or sorry, it's saying just equal. So the allowable, okay. Oh, so we're getting the highest and lowest. So that's why they're using equal. The distinct values, not a range. Equals 0.03. That's what we're saying is the max distance, the absolute value of the distance. It can be positive 0.03 or negative 0.03, but that's the difference. And then this is just basically our, this is our equation for that difference in weight. Now, how does the 36 factor? And we see the 36 being this guy being divided, or we see it being multiplied down here. So the question is, how does this play out? Which one of these is correct? So we want to know how the weight all varies out. Now, this is, then I got to think about this for a second. So we got the weight of this guy, and we're saying the individual weight has to be within 0.03, and then we take that range. Well, let me think about it for a second. And then we take this and we multiply it by 36. I think that is how you do it. I don't think you divide, but let me think. I have to think about this for a second. So we have 5.76. So let's see if this actually works, because we can actually calculate this. It's 36. This is my way of testing this. We take 36 times this, 36 times this, and this is a non-calculator section, so we got to be a little careful. Well, we can do some estimation anyways. I'm going to multiply it by 0.2. I'm going to do a quick fix. So 0.2 times 36 is 7.2. And then 0.13, let's see if I can do this. 3.6 plus 1, so I'm going to say 4.6 at the bottom. Roughly, it should be between 4.6 and 7.2. 4.6 and 7.2 ounces. All right. And let me just see if that makes sense here. 0.16. Oh, no, the decimal's got to be over. 0.46 and 0.72. Nope, that's not right. I think I had it here because 36 is... Yeah, no, I had it right. 4.6 to 7.2. This is the range. Kind of going in between here. Now, what we will get over here is... This would be 1.9. No, but this sets us equal to 3.03. So this is kind of weird. So this wouldn't actually work. And let me think about it for a second a little bit more. Because what would happen here is we want this value in here to be forced to equal So what we need, how would this work here? Oh, I see. 5.76. I see what they did. So you have to basically, they multiplied. Yeah, the way I set it up doesn't work because you need a value in here. See, this is so weird. You need a value in, you need this guy to be amplified as well. That's the problem. So I need to multiply this times 36, which I'm sure is 5.76, but let's try it out just to be safe. All right, 6, 36, 9, 0, 18, 1, 3, 4, 6, 7, 5, and then 2, 5.76. So now let me logically process this again. So we have, so it's W minus, this is the mean, or the, general weight. Again, this difference will still be 0.03 allowable weight W of a package. Allowable weight W of a oh, wait a minute. For W minus 5.76. So this is the difference of the weight, and then we have to divide it by 36. See, because this is, you know what? I completely misread this. This is a hard problem. This is the weight of the full 36 package, right? So I was thinking it was the weight of an individual candy. That was wrong. So we have to be weight minus 7.6, and then we need to divide it by 36, and that has to equal 0.03 because we actually then have to get the per candy difference, not the per unit difference, not the total difference of the box. This is actually way simpler than I thought if I would have just read this correctly. So I believe this is our winner right here. Let's give it a shot. Let's see if that's right. Okay, cool. That one works. Hopefully I didn't fumble with that explanation too much, because again, guys, I'm doing these problems live. I'm working them out on camera, which I think is in a lot of ways, it's just the most honest, and also the best way to teach is have you watch me go through the process as well. So hopefully that was helpful. Thank you guys so much for joining. Make sure to subscribe if you want more up-to-date information on the SAT, more practice problems, and of course more math music videos. I just dropped one this weekend on the equation for circles, which would be really helpful if you are taking the SAT or ACT. They seem to love those questions lately. Thank you guys so much for joining. Sorry for this late live stream, but I just had a very long day. And best of luck. See you guys next time. Take it easy.